Thanks very much. This is a really great meeting. Thanks for organizing it, everyone. And it's on to the future. This is great. So the key thing I wanted to talk about here in this and the following talk is essentially the stratigraphic context for the South Circumpolar region. It's really an exciting place to explore because we've never been there before, really. And I want to talk about this in the relationship to mapping, geological mapping, site selection, and exploration strategy applications. So this is really important because, next slide, please. It's key in terms of the reasons we're going to the South Circumpolar region. First of all, we need to explore outside the Apollo, Luna, Chang'e 3-5 exploration regions. Okay, it's really critical, and also there's tons of fundamental scientific questions. We haven't really talked about those in detail here, but transformative lunar science questions that can be addressed in the South Circumpolar region. And of course, from a strategic point of view, we need to be able to essentially survive lunar night. That's one of the reasons we're going to the polar regions. Don't make no mistake, it's not just about volatiles, it's about surviving lunar night. If we're going to stay there for a long time, we have to do that. We haven't solved that problem yet without permanently illuminated regions. So, that'll be solved in the next couple of weeks, but a couple of weeks in the next couple of years. And the other thing is, of course, possible volatile resources to support long-term human stays. This is really important, but and scientifically, it's critical, okay, did they come from the internal, external, or whatever? What's the relationship? Where does this material come from? Before we use water at the poles to flush toilets in the base, we need to really study it in detail, okay? But, what if we drill a dry hole? That's a possibility. So we need to be thinking about these things in a broader context as well. Next slide, please. So a couple of things to think about here. Our basic geological map, with 70 degrees south to the pole, is what we think of as the bedrock geology of the South Circumpolar region, as it is on the moon, of course. It identifies a major sequence of events, and I'll talk about this in the next talk. We assess what this means for addressing the fundamental scientific questions, and then how these influence human robotic exploration strategy. Next, please. This is really important because, we're not in Kansas anymore, okay? The South Circumpolar region is fundamentally unexplored. It gives us access to the far side and also to major terrains as defined by Brad Jollop and colleagues, the far side Highland terrain and the South Pole Aitken terrain. Really, really important because we talked about this at the endurance workshop last week. We're dealing with kind of half the knowledge, half vast knowledge for a vast object, which we really have concentrations only in the near side and parts of the near side. So we need to enhance this understanding of crustal stratigraphy and magma ocean heterogeneity. How can you have knowledge fundamentally of this without actually looking at the other half? Okay, this is really, really important. It provides access to mantle samples, major insights into chronology and flux of not just SPA, but dozens of craters and basins. So that's one of the reasons we compiled this new SCR geological map that is referenced here. But more importantly, apropos of what Caleb was talking about a little earlier, we also are thinking about, okay, what do we do when we get there, okay? And so we've tried to use the geological map to look at ejecta emplacement and the sequence of events. We'll talk about that more in the next talk. But really what we're trying to do is to look at the relationships of these things in their order, the thicknesses of individual units as they interleave, and use that as a way to try to get at operations and sampling strategy. This is really, really important. And, so what are the implications for site selection and exploration? As Caleb said, next slide, please. We're not dealing with well-defined geological units, folks. We're dealing with something that, in fact, is a megaregolith. Don't think regolith, think megaregolith. So the SCR center is located within the SPA outer ring, which is great, okay? This is similar to the setting of the Apollo 15 sited Imbrium. As you can see here, mapped to Oriental, you can see 15 at the outer Rook ring, but, where the critical item here, it's more like Apollo 16 in the Central Highlands, which isn't even on this Oriental chart. It's way the hell out in the ejecta deposit. So this is really a problem because we're going to get complex impact polymech breccia dominated geology. Take a look at those two polymech breccias there. It's like you take your domu and put it in a mix master and somebody hands you the rock and says, here's everything you wanted to know, figure it out. That's what we're going to be faced with, okay? So in Apollo, basis of Apollo 16 experience, the deconvolution of complex stratigraphy requires, it's a formidable challenge, and it requires really integrated strategy for site selection, geological mapping, traverse planning, sample assessment, and analysis upon return. Next slide, please. So this is really important to think about. So there's 6 things I wanted to point out here. So geological stratigraphic framework. This gives us the framework, if you will, and it's dominated by SPA, but it's obscured and complicated by multiple subsequent overlapping events and ejecta deposit, okay? So it behooves us to look at these things individually and then try to fit them back together, because key is determining sample provenance, which is a fancy way of saying, where the hell did the rock come from in the geological context of the moon? That's really important. SPA basin ejecta, Mandeling sampling paradox. What's that about? Well, it turns out that SPA is interpreted to form obliquely. So, and we're down at the southern end, which is away from where the ejecta went. And so, any deep-seated crustal material may occur in hand sample scale, but it's more likely to be in exotics and xenoliths and polymic breccias. So we need to be able to use techniques to not just do the geology, but get the crew to find out xenoliths that might be related to mantle sampling too. So determining basin and crater abundance, absolute chronology. This is really important too, because basically, in order to do this, as many scientists who study the Apollo samples have done, we need to be able to look at the statistics, okay? A regional sample is important, and it needs to be both representative of the SCR and also to collect exotics, okay? So we need to be able to do that. Next, please. So key point here too is that secondary craters, we saw from Caleb's map and others, we see this on our topography maps. There'll be a paper coming out in Planetary Science Journal by Mike Barker and others, using new data around the South Circumpolar region, much higher resolution data for everything. And we need to really take a look at the secondary craters. We see them like the Tycho crater Caleb pointed out, and we need to have grab samples, but well oriented, that is to say, well chosen bulk samples, if you will, to be able to date those. And it's an important thing because we'll be able to get Oriental and Tycho and other things as well and add them to the sequence. Landing site selection, pinpoint landing is necessary to ensure access to the targets that we want to get to, particularly if we know that there's going to be some ejecta from one crater there. We need to go be able to have pinpoint landing. But we also need significant sortie mobility, greater than tens of kilometers, okay? Not for the walking traverses early on in Artemis 3, but beyond that. And traverse design mobility, 2 major requirements. Due to the complex geology, time at individual stations should be long, and the learning discovery curve is really intensive relative to Apollo, and mobility in excess of Apollo 15 to 70 is required to obtain the necessary representative and diverse samples. Let me go on to the next slide, which shows that.
2 minutes.
This shows the distribution that what I've done is put all the Apollo traverses and others on a central point. Apollo 11 is not visible at this scale. The red circle shows the Apollo 11, 12, and 14 missions, which were walking traverses. And you can see the traverse distance was less than 5 kilometers, and the sample weight that was returned less than about 40 kilometers, okay? So next slide shows the 15, 16, 17 missions, which were in fact, next slide, please, were in fact, okay, did I miss one there? Okay, this is 15, 16, 17, where you can see it is in excess of essentially out to 35 kilometers, okay, and over 100 kilograms of samples were returned. Last slide, please. So a critical point here is geological mapping guidelines for addressing scientific goals. For the design reference mission and CONOPS and planning, we should have long, radially oriented traverses with multiple, widely spaced, long duration stations. And a lot of learning will go on at each of these stations. We also need performance design for rovers. Apollo 15 and 17 showed that, in fact, wheel slippage, we have data on this. Check out the Vasilevsky et al. Paper. Wheel slippage data for the Lunicon, for Apollo 15, 17, and also for Lunicod operations in Kamchatka, et cetera. And trust me, once you get to about 15 degrees, big problems set in. Jack Schmidt described standing at the boulder at Station 2, which you can see in the lower right, as he said when he moved, he was treading dust. Okay, so that's something that really needs to be taken into consideration. And the paper that we talk about here with Vasilevsky et al., Mons Malapart, shows you that you can't even get up with that with a typical rover unless you go up the long axis there. Last slide, please. So the past is prologue, okay? Forward to the moon and on to Mars. Listening to the Apollo lessons is critical, but as Mark Twain said, history doesn't repeat itself, but it rhymes. So please do pay attention to our experience from Apollo because I think it's going to be very valuable in our mapping and mapping the maps out to, in fact, mission planning and operations and ultimately solving some fundamental scientific problems. Thanks.